In 1925, a French aeronautical engineer named Georges Darrieus filed a patent for a wind turbine shaped like a giant egg beater. It had no blades that needed to face the wind, no gearbox grinding itself apart from misalignment. It could spin using air moving from any direction. For a design like that, disappearing seemed strange, and yet it did. Decades later, engineers at NASA and the US Department of Energy spent a fortune trying to prove that Darrieus had been right all along. This is the story of what happened to his turbine, why it worked the way it did, and why it ended up buried in a handful of abandoned desert test sites instead of spinning on rooftops across the country. To understand why Darrieus's design mattered, you have to go back over 1,000 years before he was born. In the Sistan region of ancient Persia around the 7th century, engineers built windmills unlike anything being built in Europe. Instead of blades facing into the wind like a pinwheel, their mills spun on a vertical axis, standing upright like a drum, with walls that funneled desert gusts against one side of the rotor. It didn't matter which direction the wind blew that day, the machine turned anyway. These pain-a-money mills ground grain and pumped water for centuries, and versions of the same vertical axis design later showed up in early Chinese windmills used to irrigate rice paddies. It was a working design that sat almost untouched for over 1,000 years, overshadowed by the horizontal windmill that came to dominate Europe. In 1925, Darrieus looked at that ancient vertical shape and asked a different question. What if, instead of relying on wind simply pushing against a flat surface, the blades were shaped so the wind generated lift, the same aerodynamic force that keeps an airplane in the sky? On paper, it was a small conceptual leap. In practice, it separated a machine that gets pushed by the wind from one that actually harvests it. Darrieus filed his original patent in France that year, and it took another 6 years before the design crossed the Atlantic and was granted a US patent in 1931. If you like digging into technology that got left behind, that's basically what this channel is about, so consider subscribing. There's more of this coming. Darrieus's design used curved blades, bowed outward like the sides of an egg beater, mounted on a vertical shaft. As wind crossed those curved surfaces, it didn't just push the blade out of the way, it generated lift, pulling the blade forward in the direction of rotation, similar to how pressure differences pull an airplane wing upward. Because the whole rotor was symmetrical around its vertical axis, it didn't matter whether the wind came from the north, the east, or shifted every few seconds. There was no yaw system needed, no motor constantly reorienting a heavy nacelle to chase the wind. The turbine kept spinning regardless of direction, and because the generator and gearbox could sit at ground level instead of being hoisted up a tower, maintenance that would normally require a crane could be done from the ground. That meant lower installation costs, simpler transport, and no need for the specialized high-altitude repair crews horizontal turbines demanded. On paper, it solved several of the most expensive problems in wind engineering at once. Testing it at scale would prove to be a different matter. The idea sat mostly dormant until the 1973 oil crisis sent governments scrambling for alternatives to fossil fuel. Sandia National Laboratories in New Mexico picked up Darrieus's decades-old patent and began building test turbines at a research site in Bushland, Texas, eventually scaling designs up to over 100 feet tall. Engineers there ran the rotors through years of wind data, convinced they were watching a genuinely competitive alternative to conventional turbines take shape. The Department of Energy funded the research through the late 1970s and into the 1980s, and the clearest proof of concept came out of Canada. In 1988, at Cap-Chat on the Gaspé Peninsula in Quebec, engineers switched on the Éole turbine, a Darrieus-style vertical axis machine standing nearly 100 meters tall. At the time, it was the largest wind turbine of any kind on Earth, built to prove at full utility scale that the ancient Persian shape reborn through 1920s aerodynamics, could outcompete anything with 3 spinning blades. Cyclic fatigue loading, the repeated stress and release each blade endures with every rotation, was a real structural weakness of the Darrieus shape at large scale, cracking metal from the inside long before any damage showed on the surface. The Éole turbine's actual failure came from something more sudden. In 1993, a severe storm swept through the Gaspé Peninsula, and the turbine's mechanical brakes failed during it. Without them holding the rotor in check, the machine was driven into forces well beyond what it was engineered to survive, and the resulting stress tore through the main bearing, leaving structural damage severe enough to end operation. The turbine was retired shortly after. There was also a subtler problem behind the wind from any direction pitch. The turbine often couldn't start spinning on its own. Depending on where the blades happened to stop, the aerodynamic forces could cancel out entirely, leaving a multi-ton machine sitting motionless in a stiff breeze until something else kick-started it. Horizontal turbines didn't have that problem. By the time the Department of Energy's research funding dried up through the 1990s, the wind industry had already standardized around the 3-blade horizontal design, which was better understood, easier to ensure, and easier to manufacture at scale. No single decision killed the Darrieus turbine. A storm, a brake failure, and a funding landscape that had already moved on did that instead. Disappearing from utility-scale wind farms didn't mean the idea was forgotten. Small vertical axis turbines built on Darrieus' original lift principle are still made today, marketed for urban rooftops and turbulent direction-shifting environments where a conventional turbine struggles. They're supposed to be quieter and better suited to messy airflow than a horizontal design, though the results have been mixed. Mounting a spinning mast directly onto a building structure introduces real vibration into the roofline, and the same turbulence these turbines are supposed to tolerate can also make their output wildly inconsistent, since urban wind rarely behaves the way a wind tunnel test predicts. That's a big part of why, decades after Darrieus' design was reborn for the residential market, you still won't find them on most rooftops. The idea survived. Widespread adoption didn't. Darrieus' turbine was built on a 1,000-year-old idea, patented in France in 1925, brought to America in 1931, proven at the largest scale imaginable in 1988, and lost to a storm in 1993. The physics never failed. The metal just couldn't survive its own design at full size. A lot of what this channel covers turns out to be exactly that. Technology that worked and still works in smaller forms, but lost the race for reasons that had nothing to do with whether it deserved to win. If you want more stories like that, subscribing is the easiest way to catch the next one. And if you want to see how a stack of clay pots can make a home 50% cooler without a single watt of electricity, that video, How Clay Pots Can Make Any Home 50% Cooler Without Electricity, is up next.